seat as the lead architect for a massive food delivery platform. You've got hungry customers desperately refreshing their apps, restaurants getting absolutely slammed with tickets, and delivery partners trying to navigate rush hour traffic. The stakes? They're incredibly high. If your system glitches for even a single minute, you aren't just losing data, you're leaving real people hungry and dealing with a massive logistics nightmare. So, how exactly do you route millions of meals flawlessly without dropping a single order? To really wrap our heads around this challenge, we have to look at the sheer scale of it all. We are talking about handling tens of millions of active users. And the critical constraint here isn't just the raw volume of food orders, it's the browsing behavior. Think about it. People love to window shop for food. They'll browse through dozens of menus before finally committing to what they want. This means your system's reads are massively outnumbering its writes. You need an architecture that can instantly serve up thousands of menus and search queries concurrently without breaking a sweat, all while securely locking down the relatively smaller number of actual checkout transactions. Welcome to this explainer. Today, we're diving deep into the senior-level system design blueprint of a Zomato-like food delivery platform. Our goal here is to demystify exactly how you architect for this kind of extreme scale. We're going to break down the structural choices, the data strategies, and the fail-safes that keep the meals moving. Here's our game plan. We'll kick things off with system scale and core topography, move into data strategy, and then physically follow the journey from discovery to checkout. After that, we'll tackle dispatch and delivery, event-driven choreography, and wrap up with system resilience. All right, let's jump right into section 1, system scale and core topography. So the chaos of the real world eventually has to funnel into our back end. And we've got 3 totally distinct user flows happening all at once: the hungry customer, the busy restaurant, and the delivery partner on the move. Each of these actors interacts with the platform differently. They have different peak times and entirely different latency requirements. To handle this without creating some giant, fragile monolith that falls over at the first sign of traffic, the architecture funnels these inputs through highly specialized, event-driven microservices backed by very specific data stores. Now, to prevent these distinct flows from accidentally taking each other down, the topography is broken into isolated domains, or what we call pods. We have an API gateway sitting right at the front, acting as the traffic cop. It routes incoming requests to the discovery pod for searching, the core pod for building carts and placing orders, and the fulfillment pod for dispatch and live tracking. The absolutely crucial point here is isolation. Let's say a massive surge in restaurant searches temporarily overwhelms the discovery pod. Because of this isolated design, it doesn't crash the core pod. Customers who are already at the checkout stage can still safely pay for their food. Limiting that blast radius is fundamental to high availability. Moving right along to section 2, designing the data strategy. At this level of traffic, you absolutely cannot just use one giant database for everything. It simply won't work. Instead, architects use a polyglot persistence strategy. That's just a fancy way of saying we match the database to the exact workload of the microservice. For instance, PostgreSQL is used for the core pod because it handles the strict transactional state of orders and payments. You literally cannot afford to lose a single byte of data. But for the discovery pod, OpenSearch is utilized, since it's optimized for lightning-fast geospatial queries. Redis gives us the ephemeral speed we need for temporary shopping carts and live GPS locations. And finally, Apache Kafka acts as the central nervous system, handling all our decoupled asynchronous workflows. Now this brings us to what's essentially a consistency teeter-totter. It represents the ultimate balancing act of system design. Honestly, the most important design choice you'll make here is separating heavy, locked order execution from fast, fluid viewing experiences. When a payment processes, you need strong consistency in Postgres. Every node in the system must agree that the order is paid. But when a restaurant's star rating updates, or an ETA is being calculated, eventual consistency via Kafka or Redis is perfectly fine. Decoupling these 2 types of data states is the secret sauce that allows the platform to feel instantly responsive to the user while remaining completely financially secure behind the scenes. Let's see this in action in section 3. From discovery to checkout, we're going to follow the actual user journey. Every journey starts with a search. When our hungry user looks for North Indian food within 5 kilometers, that query completely bypasses the heavy relational database and hits OpenSearch directly. OpenSearch is built exactly for these complex geospatial queries.
Yeah.
Once they select their butter chicken and naan, that data goes straight into a cart service powered by Redis. Because Redis is an in-memory data store, adding items feels
Historically, they could have gone either way, but they went the
pay
other
attention
one.
to this key security detail.
There was a big debate
While the
as to
cart
whether
lives
use
in
this
Redis,
king as a
the
scapegoat or
subtotals
not.
are always calculated server-side by checking the central menu service.
not gonna have
You
range
can
for
never,
that.
ever trust the client app with prices. If you did, someone could easily spoof a request and buy a steak for a penny. Okay, let's dive into a concept that literally saves companies millions of dollars. Imagine your users on a really spotty 4G connection on the subway. They hit the place order button, but their connection drops before they see the success screen. They panic, right? So they mash the checkout button 4 more times. How does the system prevent them from accidentally buying 5 identical pizzas? It uses an idempotency key. This is a unique ID generated by the app for that specific checkout attempt. When the order service sees 5 rapid-fire requests coming in at the exact same key, it processes the very first one. And for all the subsequent
Mark,
requests,
that's
it simply
what-
returns
Yeah.
the successful
Lend-Lease he
state,
sent me is
ignoring the
monthly,
duplicates entirely.
is monthly
Now,
on
creating that
everything,
order
and then
safely
you only
requires
send one.
coordinating the
Right.
database and the event system perfectly. And we do this using the transactional outbox pattern. When the user checks out, the system doesn't just write the order to the PostgreSQL database and then try to publish a message to
I'm
Kafka
guessing,
separately.
are
The
we
database
joining the war
succeeds, but
against
the network fails
Ethiopia?
Before hitting Kafka, your systems are suddenly out of sync.
you
Not
can,
good.
I was
Instead, in
mistakenly
one
did,
single
but
atomic
that's-
transaction,
so
the
obviously
system writes the order details to an
Later
order
on.
row and writes the event
have I-
payload to an
Have I done
outbox
something
event
stupid?
table
Oh, I have
in
done
that
something
database.
stupid. No
A
wonder.
separate background process then safely
I wouldn't
reads that
because it's probably
outbox
messed up
table
the,
and publishes to
array.
Kafka.
Did you do?
This guarantees that if the database commits,
I was
the event will
wondering why they were
absolutely
trying to
eventually
travel
be
halfway
published.
across the world.
Before we
It's
leave the
because
core
for some
data
reason I had
I want to
them
highlight
on
a crucial detail in the order items entity.
region in
The
the
system doesn't
Mediterranean,
just store a
and they were
reference
trying to
the
reach it
item
from
ID. It
Eastern
actually stores
Micronesia.
an item name snapshot and a
Why
unit
don't
price
you just set
snapshot.
automatic
Why?
ports?
Because of historical integrity.
Automatic combos.
If a restaurant decides to double the
better
price of their
on
burger
Cyan.
tomorrow,
Yep.
you
And
definitely
AP,
don't want
so
yesterday's
Cyan's now
receipts
on
to suddenly
Copro.
update and reflect that new price.
No, it's
Storing
fine.
snapshots
You
ensures
just
that
have-
past orders remain perfectly accurate financial records, totally decoupled from any future menu updates.
Oh,
Up
yeah.
next is Section 4, Dispatch, Tracking, and Delivery. This is where we tackle the hardest physical problem, moving real food to real doors.
Confused again.
So, the food is ready. The dispatch service uses Redis
That's New
geospatial
Zealand.
data to find nearby drivers.
Now
But
that's
here
busy
we run
burger
into a massive concurrency
Oh.
issue. What happens if two
How's that one?
totally different
Yes,
orders try to
it is.
claim the exact
Should
same
wait till I
delivery
need them.
partner at the exact same millisecond? Atomic SQL locking
Oh my
solves this
God,
perfectly.
I'm very
The system
rich.
runs an update query to assign the order,
Right.
but it appends a really strict
I'm getting
clause,
50% of all
and
this
status
production on
equals
all the
available.
vehicles that I want.
Because Postgres guarantees atomic
Oh.
operations,
You'll
only
use
the
it
very
better than I
first
will.
request will see the status as available and succeed.
Because I don't
The
know what I'm
simultaneous
doing.
second request will see the status is already changed. It'll fail to get the lock,
in
and
theory, you
it
could
creates
set
time
up
to find the
10%
next
of your
nearest driver.
production to Belgium and 10%
Once a
Someone-
partner
production
is
to
actually
me,
assigned,
and then
the
we
order
obviously
moves
set
through a
like-
very strict sequence of
someone
states,
send
and these
me
transitions
more
have to be
coffee?
rigidly enforced. You cannot have an order
And-
jump from accepted
Okay, I'm glad
straight to
you can.
delivered without being
I
picked
can
up
send you some
first.
covers,
This
actually,
is managed
that's
using
better.
optimistic locking with a
I'm
version
gonna
column in the
embargo
database.
Japan.
Every time the status updates, the
Because I'm
version number
using
increments.
500 just for
If a
my
rogue
Lend-Lease
network
from
request
America.
tries to update an older
Oh,
version
no,
of
I
the order,
lost
the
another battle
database
cruiser.
outright rejects it. This protects the physical reality of the delivery from digital network hiccups. Now, as the
I'm
driver
actually
speeds
also
toward the
using
customer, their app
400
is
for that
blasting out
America.
GPS
But I
location
have,
updates every
64
few
that I'm
seconds.
doing not-
This massive fire hose of data gets split.
All right, I'll send you
The
another.
Okay,
latest,
that's
freshest
absolutely
location is written
fine.
directly to Redis. Redis then instantly pushes that pen down to the hungry customer's app via a WebSocket connection, giving them that smooth, live tracking experience. Simultaneously, a portion of that route data is sampled and sent over to Kafka. Kafka stores it for the long term, so analytics
need
teams can
convoys
use
to
it
trade
months
with
later
Congo.
to train machine learning models for even better historical
My
ETL
issue is
predictions.
I have to
Let's step back and look at the bigger picture.
Yep.
In Section 5, Event-Driven Choreography.
Oh, thank you.
And this brings us right back to Kafka.
Assalamu alaikum
Instead of having a
warahmatullahi
master
wabarakatuh. That
orchestrator service micromanaging every single step and slowing down the checkout process, the architecture uses choreography. When an order is placed, the core pod simply drops an order-placed event onto the Kafka event bus and moves on. It's done. Now all the other services are just listening. The search service hears it and updates the restaurant's popularity index. The notification service hears it and triggers a push alert to the user's phone. The analytics service logs the metrics. This completely decouples heavy background tasks from the critical latency-sensitive path of the user actually buying their food. Finally, we reach Section 6, System Resilience and Observability. keeping the lights on. Every senior system has a resilience playbook because high-scale systems are literally designed for failure. For instance, what if that live WebSocket location service we just talked about completely crashes? Instead of throwing up a giant error screen and panicking the user, the app implements graceful degradation. It quietly queries the core database for the last known location and displays that static pin, maybe throwing up a friendly message saying driver is on the way. The core mission, getting the food to the door, proceeds uninterrupted, even if the fancy live tracking bells and whistles temporarily go down. But when things do break, you absolutely need to be able to find out exactly where the chain snapped. When you're dealing with dozens of isolated microservices, looking at isolated server logs is basically like looking for a needle in a haystack. This is why a single unique request ID is injected right at the API gateway the exact moment a user initiates an action. That ID is passed along in the headers to every single microservice, database call, and Kafka event downstream. This gives us end-to-end distributed tracing. Engineers can query that one ID and instantly pull up a visual waterfall of exactly how long the request spent in search, how long it was in Redis, and exactly which line of code threw an error. Let's wrap things up with this golden rule of food delivery architecture. Design around the order lifecycle. Decouple execution from experience. We've seen how locking down the crucial financial state in PostgreSQL allows the rest of the system to be wildly fast and eventually consistent everywhere else with Redis and Kafka. Decoupling ensures resilience. It allows the architecture to flex, scale, and occasionally fail without ever dropping a customer's meal. So as you look at the systems you are building today, ask yourself, where are you needlessly binding your fast, fluid user experiences to your heavy, lockdown execution paths? Untangling those might just be your key to scaling to the millions. Thanks for joining me on this explainer.